And now let us move on with the next speaker, who is going to talk to us today about how we can apply deep learning elements for tabular data processing, because we know for sure already that for some tasks like text processing and image processing and sound processing, deep learning models can really make it all a day, and the learning will improve by hundreds, by dozens of hundreds of percent. And I.Bondarenko is going to talk to us about deep learning for tabular data processing. Good evening, colleagues. So my name is I.Bondarenko, as I have been introduced, and I would like to talk about an unusual topic and combination as AutoML and deep learning for tabular data processing. So separately, these components are pretty compatible: AutoML for tabular data and deep learning for tabular data, deep learning with AutoML. But deep learning for tabular data is something interesting. Like Alexander has said, deep learning and neural networks do it all in CV and text processing. But as for tabular data, boosting is our role, but I would like to discuss with you whether it is truly so or not. To begin with, I would like to tell you a couple of words about myself. My name is Ivan. Like I have introduced myself, and I am interested in machine learning. I've been interested in machine learning since 2005, 2006. I used to work in academic sphere, and I worked in the university. Then I followed up with the IT industry, and I worked as a data analyst, and I mainly focused on speech recognition and text processing. That is the largest area of my work in ML. And starting with 2020, I joined Huawei, and I focused on tabular data processing, because the task that the company has is connected with developing AutoML for big data that are not pictures, texts, or speech, but they are structured tabular data. What can be done in this sphere so that users who are not experts in AutoML or just any kind of ML could successfully upload their data and receive good solutions to be used in their business? Retrospectively, computer vision has the main tasks of machine learning and image recognition with classical architecture and classical pipeline of computer vision in the following way. For each specific task of recognizing features, maps, cars, there was a special feature engineer who sat to develop approaches to feature extraction and classification through usually classifier with some shallow structure, not a neural network, made a final decision on the recognition. This approach, on the one hand, could provide for pretty good efficacy, but on the other hand, the system of features developed for a specific task could not be used in another task. And the development of the feature systems, so the labor of feature engineer was really very long and labor-intensive. This scheme was pretty successful in image dataset, which is very well known, ImageNet dataset, and there is recognition of images on a very large datasets, and all amateurs know it very well. That is over 14 million images and over 20,000 detailed categories, and that is around 1,000 hyperonyms, the more generalized categories. And the solution that showed pretty well in 2010 and won some competition was based on classical pipeline of computer vision. It was a complex, multi-stage feature engineering, and support vectors for final decision making. The correctness of recognition getting to top 5 was almost 72%. A little bit later, other approaches were put forward based on deep neural network. The particular features of these approaches were that we do not make a structural pipeline. We say, dear neural network, you are a multi-layer one, so you can decide yourself which features are significant, which are not. In the input, there are raw features, and you have multiple layers, you build hierarchical representations on features, so please do it for us. So the approach based on deep neural networks with a minimum feature engineering, or with the absence of feature engineering, has proven much better. And the winner of this competition at ImageNet of 2014 was the convolution network, whose quality was much higher. There was no manual labor, no feature engineer that did something, but automatically the feature engineering performed by layers of deep neural network turned out to be better than manual feature engineering. Why did it so happen? Why do convolution neural network why are they good for CV? First of all, like I have mentioned, deep neural network, including convolutional neural network, build hierarchical feature representation. The younger or inferior layers show inferior features, simpler features, and the closer we get to the end of the neural network, the more complex, object-oriented, high-level features are identified in layers, and therefore we have layer-by-layer hierarchical representation. Therefore, we take this feature engineering to the automatic algorithm, and feature engineering components and final classifier, the last layer of the neural network, are trained together by one algorithm, and I believe that is the most effective method of optimization of gradient method, and that is the success factor of computer vision. Is it only applied in computer vision? In speech recognition, we can see the same picture.
The first architecture of speech recognitions in late 80s, early 90s were based on components. So it started with acoustic phonetic submodel that would identify attributes of the speech signals and recognized phonemes. Then there was the linguistic block, manually built up, and pronunciation dictionary, or generated by transcription rules determined. And this component architecture, it represented the idea of linguists about the structure of speech in the 90s. Then later in 2000s, 2010s, so the architecture became more complex based on some simpler neural networks, 2D convolutional networks. Look at the picture. And finally, in our days, in recent years, we see the domination of deep end-to-end architectures. No components, no pronunciation dictionary, no separate language models, separate from acoustic models. Well, there are some, but the neural network can work independently. So I showed you Jasper architecture. We see the domination of back-to-back based on transformer in speech recognition. And it happens to natural language texts. At first, it began with thesaurus, linguistic ontologies, or other solutions. But recently, in recent several years, we see the Elmer transformers looking like bird. Neural networks have gained popularity. This wonderful picture, and I would like you to pay attention to the fact that, in my opinion, as other people think, domination of neural networks was due to their depth that allows to transform language by hierarchy, and you can transfer learning process using same attributes for similar tasks. As for the tabular data, why don't we see dominating of deep learning in tabular data, like in other areas where machine learning is used? This is an example of tabular data. We have a target, we have a lot of inputs, and there is one important detail we take from deep learning to tabular data analysis. Our data have no local ordering. If we would look at the picture, we see that the darkness, the lightness of neighboring pictures change significantly, and the structure is important here. If we would take speech recognition, so we see that the energy by frequencies in time changes, but the process is smooth, so localization is important. If we take tabular data, the order of columns doesn't really matter. So they can be 1 to 3 to n, or we can mix the order. Nothing changes. So the structure is not relevant. That's why, in opinion of others, neural network proved to be efficient for computer vision, speech recognition. Convolutional neural networks, due to different kernels, can identify different structural data, and it doesn't happen with tabular data. And that's based on this concept. We built two approaches to the for classification and regression of tabular data. First of all, we have input attributes. It's a complicated engineering, complicated feature engineering plus simple linear models. Or otherwise, it's simple feature engineering with simpler nonlinear models, like tree-based models and k-neighbors, a simple method, but a working one. If we would talk about a complicated feature engineering, manual feature engineering doesn't work all the time, and we need a solution for an automated baseline. So automated feature engineering can help. It was the method of deep feature synthesis, one of the first sparrows. There were operations on aggregating data in tables. There are different types of tables, like reference tables, and different combinations of aggregation. We're working here. We don't try to evaluate it. Once we applied it, we use an algorithm with the hope that objects will be more dividable. Another approach on a smarter feature crossing used some algorithms with an assessment of space attributes. So attributes passed the discretion for a number of intervals, and finally they were used for reinforcement learning. When we build a graph of calculations, we can sum or retract them. We don't know what would be the best for optimizing space attributes, but this is a classical solution for reinforcement learning. I think that such approaches to automated feature engineering are really used there. If we would talk about tree-based models, then there is assembling, random forest. It offers more durable solutions than separate individual trees, but gradient boosting, and my colleague already told about it, so it offers higher quality of solutions than random forest. In some cases, methods based on nearest neighbors are working. The problem is different. The data sampling is simple, but you can optimize it with the nearest neighbors, like in the case of Spotify. And finally, a classical approach to AutoML for tabular data that combines all the tricks, all the methods for feature engineering. The last example for the pipeline, and there is an article dedicated to reinforcement learning. There is like a data preprocessor, feature preprocessor, and a regressor. The pipeline method is combined with the regression, and you need to use Bayesian search. If you have a diagram or a pipeline, if it was successful for some data sets, you need to first identify the best class of data sets and say what diagram would be used. For other class of data sets, the other one would be working, and so on. And then we would ensemble. After skip-learn, after auto-waking, there were other examples for reinforced learning, but I would also like to pay your attention that algorithms related to trees and k-nearest neighbors, they have a number of limitations. Have a look at this picture. At the left, you see a simple example of regression task resolved by linear regression trees. And in the middle and at the right, you see more complex solutions, but you see that the decision tree methods and the k-nearest neighbors are more accurate, but you have the test task for tomorrow, and it's different. So linear regression is more adequate in showing the trend compared to algorithms based on decision trees and k-nearest neighbors. They cannot do the extrapolation. So that's the case with the decision trees, and linear regression can resolve tasks like this. And what about neural networks? A neural network is a tool of non-linear regression. So maybe going back to neural networks for processing tabular data, we can be more efficient. One of these first sparrows where neural networks were used, it was AutoGluon. AutoGluon is a framework for AutoML for general use. It used a number of methods of gradient boosting, like k-neighbors methods, and also you see like something like ResNet, where features were encoded by embedding, and you see how it looked, the neural network, with some other elements of ensemble, with some levels, bagging, stacking, and the ensemble would take the final decision. And back in the days, AutoGluon was state-of-the-art. Now in AutoML, now it competes with H2O, with some models of gradient boosting for neural deep learning, but the progress didn't stop here. One of the most funny and extraordinary articles I read about was about the method for classification of tabular data using convolutional neural networks. So convolution is generated here to unveil an anchor image. So here you see the rows in this case, and then convolutional layers of the neural network, like in the case of ResNet. And as authors believe, different rows are unveiled differently. It's a very interesting article. Personally, for me, it's interesting because the idea was offered. Let's analyze the task with tabular data differently from an AutoML task. Let's try to do the learning transfer. Because we have resources on ImageNet, but it was really, it would be something odd. Another article from 2020 on TabNet. So the method, all you need for speech recognition, also visual transformers, and here there is a model with attention for analyzing tabular data. So it's written about transformers, but they are not conventional transformers looking like bird. It's not a neural network, but rather attention is used to localize a group of attributes which are most important for every stage of decision-making. So authors try to combine the best points, the best features of deep learning, and it's focused on groups of transformers. Is it can learn itself, and as authors think that fading out of neural gradients can also be applied, and this scheme is the best for tabular data analyzing. And the results with their experiments proved to be better than with other algorithms, including those based on gradient boosting. There are a lot of parameters. It's a question on how many steps of transformation and how many steps are required for feature transformation. With attention, it's clear. it's based on sparsing. If you would read the article, it's for 13 pages, and for different data sets, different hyperparameters were chosen. And it's a question whether it's an all-round solution. But at least it looks very interesting and promising. I'd like to remind you that we began by saying that a deep neural network is an efficient hierarchical transformer, and that's its strong side. But the problems, the downsides it can have, it's very much oriented on local data structure, and they are common for convolutional or recurrent networks. And there were some steps made to overcome those downsides. Local network with attention, and I think such research works are promising, but at the moment I cannot say. Let's use deep learning, and all other approaches to tabular data are outdated. There are a lot of questions related to deep learning for tabular data. Is a neural network for tabular data a production-ready solution? And if they are durable to competitions, data shifts, and adversarial attacks, like fast gradients, SIM. Also, what happens with computer vision? Is it really relevant for tabular data? And opponents of using deep neural networks, so opponents mentioned their explainability. They doubt it. However, it's possible that we are at a dawn of a new revelation when the last tower of machine learning will fall. It's exciting, and I'm trying to be part of this revolution, and I would be happy if you, dear colleagues, will take part in it as well. Many thanks, dear friends. I am ready to answer your questions if you have them. Thank you, Ivan. Thank you for your presentation. There is one single question. If you, based on your experience, can describe the group of data sets for which you will use the deep learning models together with the classical machine learning. Thanks for your question. There is the theoretical side and a practical side. In theory, you can use deep learning for all types of data sets. We all know the theorem about the data sets as being a universal tool for neural networks. But in practice, data sets with a big number of features can be not very much successful. And for sure, you need to use learning embeddings, but attributes should be normalized for neural networks. It's very important just to avoid problems with learning and gradients and signals. If we use ReLU, there is a problem with a lot of cleared data. It's about normalizations in the style of batch norm and input data. As if you remember article, efficient backprop by Likun, and it shows that the neural net is efficient. I would also like to mention one side of neural networks, and I didn't mention it in my presentation, self-normalized neural networks. I'm talking about how gradient is distributed in neural networks, so it can fade out. And normalizations like batch norm helps with some features. For convolutional networks, it's not that important because shared weights are used, but for fully linked neural networks, it's not that bad. So we can say cautiously that deep neural networks are used for data sets of different types. Understood, Ivan? So really, there were some very interesting ideas in your presentation. So let's forward. And what comes from your team for AutoML benchmarking? So it's good to find it for some segments where it would be efficient.